Right, maybe we should start the lesson right now. And we are coming back to the lecture note set number 4. And in Monday's lesson, we have been talking about the first law of the thermodynamics. And of course, it is just the conservation of energy. And at here, we would be focusing quite a lot on the specific case of the first law of thermodynamics applied in a gas system, where you would expect the presence of a few energy terms, which the energies could be calculated by relatively simple means without deducing what is inside from the, for the case of the, say, liquid or the solids, where the internal energy would be a very complicated situation due to the interaction of particles. We will be focusing on the ideal gas, where the energy, as we will see later, depends only on the number of gas molecules as well as the temperature in the absolute scale. So at the beginning, we established the connection between the work done and heat, which are some energies that would be transferable between the system and its surrounding. So you have a several types of energies that are involved. And the first one is the internal energy, which is due to the internal motion of the atoms in the system. In the case of gas, it mainly concerns with the kinetic energy, although the kinetic energy could also be complicated due to the various types of motion. You have a translational motion, and if you have multiple atoms in the molecules, say nitrogen molecules or oxygen molecules, you could have rotation about the center of axis, as well as the vibration due to the presence of the temperature. So things are never very simple. And if you have other types of interaction, the calculation of internal energy is hopeless. And therefore, we are just focusing on the case of the ideal gas. Heat is another type of energy which is only present when you have a system and the surrounding. You have the heat which flows between the surrounding and the system due to a temperature difference. Of course, it is up to you to decide where is the system and where is the surrounding. It may be originally one gas, but you may have two parts. So in that case, you may treat one part as the system and the other part being the surrounding. So you could have a flow of the heat energy from one side of the system to the other side. So it is a kind of a arbitrary definition. But the concept of heat is not arbitrary at all. You must have a flow of energy due to temperature difference from one side of the system to the other. So that is the idea of the heat. Internal energy, on the other hand, is always present within the system. And right. And we have discussed about the effect of the heat energy on the state of a system. In particular, when you put a heat energy to a system, it could lead to different situations. For example, you could increase the temperature of the system. Say a gas or a liquid or even solid, when you put a heat energy to it, it could increase in temperature. And that is the idea of the heat capacity introduced in this slide. You have a system that when you input a certain amount of heat energy, and it will increase the temperature by 1 degree C. and that would be the heat capacity. In order to make it even more general, you could divide the heat capacity by the mass. So this, what we call specific heat, becomes a material dependent property. And the specific heat is defined as the amount of heat energy, required to raise the temperature of 1 kilogram of the substance by 1 degree C. So Q divided by M delta T is the equation for the specific heat. Of course, heat is an energy, so it has a unit of a joule, and M has a unit of kilogram. Delta T has the unit of Kelvin, or equivalently degree Celsius, because a change of 1 degree C is equivalent to change of 1 Kelvin of a temperature. And whenever we are putting energy into a system, you expect the temperature to increase, and therefore Q and delta T would become positive. When you are taking away heat energy from the system, Q becomes negative. So that is the usual sign convention we will use. Specific heat of water is some important concept. It has a relatively high value compared with many other types of materials. So it is responsible for a lot of natural phenomena, such as the the smaller change of the temperature in the regions close to the sea compared with the inland area, due to the higher specific heat of the seawater compared with the land. So the land, which is made of rocks, can lose heat and gain heat much more quickly when exposed to the same amount of heat energy. So that is the idea. The study of the flow of heat energy, or the measurement of the specific heat, is referred as the calorimetry. So the idea of the calorimetry is that you try to put a certain amount of a substance into some liquid, for example, water, of known temperature and mass. By the transfer of heat between the water and the substance, and assuming no heat energy transfer, conservation of energy takes place. So amount of heat energy gained by the cold system is equal to the amount of heat energy lost by the hot system. So you have this equation: Q cold equals to minus Q hot. Q hot, which is the heat energy lost by the system, must be negative. So you put a negative sign in front of it to balance the two sides of the equation. So in terms of the equation form, this would be the one. Of course, when you have just one single phase of the substance, there would only be a change of temperature when you put in or remove heat energy. On the other hand, if you are coming to the freezing point or boiling point of a substance, addition or subtraction of heat energy could lead to a phase change. When you are changing from solid to liquid, or from liquid to gas, you have to input heat energy. No temperature change occurs at that process. During the phase change, there is no heat, there is no temperature change, but heat is transferred to the system, and the system changes the phase. Similarly, when the liquid solidifies, or when the gas is condensing into liquid, it loses heat energy. No temperature change, but heat energy is lost. So the amount of heat energy that is lost or gained is related to the latent heat. So the latent heat, it measures the amount of heat energy gained or lost per unit mass during the phase change. So that is the idea of the latent heat. Due to the possibility of melting or freezing and boiling and condensing, you have two different possible latent heats. One is the latent heat of fusion, which refers to the conversion between liquid and solid. The other one is latent heat of vaporization that correspond to the phase change between liquid and gas. So here in this diagram, it tells you what happens when you are trying to put in heat energy continuously to a lump of ice below 0 degrees Celsius. When it is in a solid form, it takes in heat energy until 0 degrees C. So it's at the left-hand side of the diagram. And then at the stage B, the ice is converted into water by absorbing latent heat of fusion. After all the ice is melted, it becomes water. So it continues to absorb heat energy and temperature increases until 100 degrees C, where once again, phase change occurs, but this time is from liquid into gas. So no temperature change, but heat energy is absorbed as latent heat of vaporization. Finally, all the water is converted into steam. So when you keep on putting in heat energy, the steam would keep on increasing its temperature. So that is the idea of heating that involves phase change and involves, well, the phase change is in B and D, and heating that involves only the temperature change, so A, C, and E in this diagram. At the end of the last lesson, we have seen an example telling you how the energy is converted when you are putting a some steam initially at 130 degrees C to water and glass, and raising the temperature of the water plus glass from 20 degrees C to 50 degrees C. So it involves the consideration of the energy involved, for example, in the phase change. Cooling the steam from 130 degrees C to 100 degrees C involves some energy, which can be used for heating up the water and the glass. And also the condensation of steam into water at 100 degrees C involves latent heat. So it is always a comparison of the total energy involved in each process to decide what is the final state, if you like, of the whole system. If you have a lot of steam, for example, you may bring the water into steam as well. And that is because if the glass plus the water is reaching 100 degrees C, of course, the glass will stay at 100 degrees C while the water is being boiled. So it depends a lot on the energy that is involved during the boiling of water and at the same time during the cooling of the steam and the condensation of the steam. Right, it seems a little bit confusing, so why not if we take a look at an example. Please take a look at the question number 5 in the tutorial set number 5. Or let me see. Now it's question number 6. Sorry, it's question number 6. Question number 6. in the tutorial set 5. Okay, so at here, it starts with a very simple situation. You start with steam, 100 degrees C, and ice, 0 degrees C. When you start with 10 grams of steam and 50 grams of ice in the part A, you are asked to find out how much ice is actually melted and how much what is the final temperature of the mixture. So how do we tackle this problem? Well, I will just show you the solution at here, so not to spend too much time writing on it. Let me see. Okay. Right, so by now you could see that here, the solution. The idea is like this. You have basically two systems. One is steam, the other one is ice. Q1 at here refers to the energy to melt all the ice. So it is easy to calculate because it is equal to M times L. So according to your lecture notes, the latent heat is L. And for the conversion between the ice and water, the latent heat of fusion is 3.33 times 10 to the 5 joule per kilogram. So this is L. Let me see. So this would be L. And this is delta. This is a mass of ice. So you could calculate what is the energy we require to melt all the ice. And you could compare it to the energy available for condensing all the steam. So the steam is initially 100 degrees Celsius, and you try to condense them into water at 100 degrees Celsius. So you could see that at here, this is the mass of the steam. And the later part is the latent heat of, well, vaporization. The latent heat at the top is actually the latent heat of fusion for the water. So you could see that Q3 is 2.26 times 10 to the power 4. Q1 is 1.67 times 10 to the power 4. What does that mean? Now, think about it. You have the ice that melts completely, and it requires 1.67 times 10 to the power 4. The energy can completely comes from Q3, which is the energy that could be given up by the steam when it condenses in water. So before all the steam condenses in the water, all the ice has already melted. Q1 is smaller than Q3. Sorry. Q1 is smaller than Q3. But at the same time, Q1 is smaller than Q1 plus Q2. What is Q2? Q2 refers to energy required to heat up all the water. Originally ice, you heat up all the melted ice, 50 grams. You heat up all the melted ice from 0 degrees C to 100 degrees C. It requires 2.09 times 10 to the power 4 joule. So this is M times C times delta T. You see. So this is a mass of the ice, and this is a specific heat of water, and the later one is the delta T. So you see that Q3 is smaller than Q1 plus Q2. And it means that before all the steam condenses in the water, before all the steam condenses in the water, before all the steam condenses in the water, you would have all the ice melted. But after you condense all the water, you condense all the steam. After you condense all the steam, the water that is originally ice has not been raised to 100 degrees C. So Q3 is smaller than Q1 plus Q2, meaning that at the end, you would have the mixture being water at some temperature between 0 degrees C and 100 degrees C. So you could guess from the first statement, Q3 larger than Q1, you could guess from the first statement, Q3 larger than Q1, that all the ice is melted. All the ice is melted. But at the same time, the final temperature would be smaller than 100 degrees C, because after all the steam is condensed, it cannot heat up all the ice to melt them and bring them to 100 degrees C. The energy Q1 plus Q2 is larger than Q3. So you try to determine what is the final temperature in this case. Q cold refers to the heat energy gained by the ice as it melts and increases in temperature in water form. So ice melting, Q1, plus the water from ice that is now in the form of water, it is being heated up to some final temperature. minus Q hot refers to the energy given up by the steam when it condenses in the water, together with the energy of the 100 degrees C water, originally being steam. Now it is lowering in temperature from 100 degrees C to some final temperature. So that is how we decide the final temperature in this case. So that would be the part A of the question. And then in part B, now you are not providing 10 grams of steam. You just provide 1 gram of steam. What would be the final situation? To see the situation, let us first consider how much energy that can be given up by the 1 gram of steam. At the beginning, Q1, energy required to melt all the ice, 1.67 times 10 to the power 4 joule, is just equivalent to what we have at the top at here, Q1. Q2 is the energy given up as the steam condensed. Now it is only 1 gram. So when the steam condenses, it gives up this amount of heat energy. What does that mean? Comparing Q1 and Q2, it means that when all the steam condenses in the water, it is not sufficient to melt all the ice. It is not sufficient to melt all the ice. So the 100 degrees C water would be cooled further from 100 degrees C to some temperature in order to melt the other ice. Now, let us see what if all the 100 degrees C water is cooled to 0 degrees C. What is the amount of energy given up? The amount of energy given up is 1 gram times 4186 mc delta T. Delta T 100 degrees C. All the steam, all the water at 100 degrees C cool down to 0 degrees C. It is only 419 joule. Adding to Q2, it is still smaller than Q1. This means even when all the 1 gram of steam is condensed into 100 degrees C water and all the 100 degrees C water cool down to 0 degrees C, it is not sufficient to melt all the ice originally at 0 degrees C. So the final temperature at the end would just be 0 degrees C because the steam is not sufficient to melt all the ice. Even when it is lowered from 100 degrees C steam into, well, even when it is condensed from 100 degrees C steam into 100 degrees C water and lowering the temperature from 100 degrees C to 0 degrees C in a water form. So how much of the ice originally at 0 degrees C is being melted? The total amount of energy available from the steam is 2.26 times 10 to the power 3. And after it condenses in the water, it has an additional 419 joule before it cools down to 0 degrees C. Total energy, Q2 plus Q3. And this would be the energy used for melting the part of the ice. So that part of the ice is M, and the latent of fusion is L. So you would calculate that the amount of ice being melted is only 8 grams in this case. So there's still around 42 grams of ice being left at 0 degrees Celsius. So that is the idea for calculating the energy transfer. You have to compare the energies involved in different phases, and you have to compare the energies involved during the heating or cooling of the single phase system in order to decide first what is the remaining situation, and second, what is the amount of ice, amount of a substance being converted, just like in this particular example. Some of your classmates is asking, in A, why could not be the case that some part of ice is converted into steam, while some part of ice remains to be water? We are talking about, well, in the part A, we have firstly ice together with steam, both at, well, the ice is at 0 degrees C. And you are talking about the same temperature. You need to be at the same temperature. You cannot have part of the system in the steam form and part of the system in the water form, unless both of them are 100 degrees C. So if you have the steam that could provide all the energy to melt the ice, then all the ice would be melted. You cannot just melt some of the ice and let those ice turn into steam, and the remaining part stay as ice or water, because you are required to reach a thermal equilibrium. Otherwise, the calculation would be kind of meaningless, because it's in the middle of the situation. Right. So let us come back to the lecture notes. Okay, we will be skipping the superheating and the supercooling because, well, they are interesting, but they are not particularly discussed in detail. So it might just well be worthwhile not to mention them at all, at least in this stage. You may be talking about it when, for example, for the case of mechanical engineering students, you may discuss about it in the more advanced course in the thermodynamics. So let me see. I have to share the screen again. Right. Okay. Right. So let us come back to the case of the gas, if you like. And when we describe the thermodynamics of the system, we are always concerned about the situation or the state of the system. The state refers to the condition of the system at the present moment. For example, what is the temperature? What is the pressure? Something we could measure in the system that describe the energy content or the parameters that is used to describe the system itself. So these parameters, we usually call them the state variables. At a certain condition, the state variables could describe the situation of the system. So these variables may include pressure. For the case of a gas, it includes the pressure, the temperature, the volume, and also the internal energy. So if these are state variables, as long as the system is not in contact with other environment where you may have a flow of energy into it, then you could specify what is the situation of the system. And when we are describing the state of the system, we usually make the assumption that the system itself, within the system itself, is in thermal equilibrium. When it is in thermal equilibrium, no matter at which location we measure these state variables, we would get the same answer. Say, when we measure the temperature at the top right-hand corner of a container for the gas, we would obtain the same result if we measure at the bottom left-hand corner. This would be essential if we try to describe the situation of the system. Otherwise, once again, if the system is not in thermal equilibrium, then it is not easy to specify the condition. So usually we have to let the system to settle into thermal equilibrium so that all the state variables would be equal within the system. And we could describe the whole system by one single parameter. So typically, in the case of a gas in a container, it usually means the pressure and the temperature at every location or every part of the gas must be identical. It is a homogeneous, uniform situation. And the state variables could be used to describe the system that is isolated without being in contact with other environment. On the other hand, there are other variables which could only exist when you have a contact with the surrounding. And these are what we call the transfer variables. Transfer variables do not exist, or you could regard them as zero, unless you have a energy transfer process that takes place across the boundary of the system. Think about heat. Heat refers to the energy transfer from the high temperature location to the low temperature location. So without a boundary, you do not have the heat transfer. And without the process of moving the heat energy from high temperature place to the low temperature place, there is no heat that will take place. So transfer variables needs to take place when needs to take place across a boundary between the system and its surrounding. Similarly, when the gas is isolated, it will not have any work done. Only when it is acting to the surrounding or being acted by the surrounding. For example, you compress the gas and decrease its volume, then you are changing its boundary. In that case, you have work done. But if you have the system that lives by itself, there would not be any work done, and there would not be any energy transfer across the boundary. So isolated system would not have transfer variables, or the transfer variables would be zero unless you have a process that takes place. In this regard, there are two types of energy transfer processes, heat and work done. They are the transfer variables. We have already discussed quite a lot about the heat. For example, how you are bringing the temperature of the system up or trying to change the phase of the system by means of the heating process. So then in the next, we take a look at the case of the work done. We learned about the work done at the first set of lecture notes. Basically, it refers to the force applied to the system and causes the displacement. And that would be the case of force applied to the particle or a solid, where we do not expect any change in the shape of the object. Things are very much different in the case of a gas, because when you press on a gas, it could change shape. But in this case, you still would impart some work done to the system. So let us take a look at this cylinder, which contains some gas. And the cylinder is sealing the gas by means of a movable piston. If the piston is not moving, it means one thing. The piston is not moving because the force from the outside is equal to the force from the inside. It is not moving according to the Newton's first law. There is no net force acting on it. Now, it is not saying that there is no force acting on it. I am saying no net force. So there is force. Where comes the force? Remember, the gas has pressure. I did not really talk about the definition of pressure, but hopefully you have learned it in the high school. So basically, when you have a container and it contains some gas particles would be bombarding on the walls of the container. So this would be the origin of the pressure. And the physical definition of the pressure is you have a force acting perpendicularly to the area. And so the value of pressure is equal to the force divided by the area. Although force is a vector, pressure itself is a scalar. The pressure is always considered to be acting perpendicularly to the area. It's always acting perpendicularly to the area. So here, the force inside the gas is coming from the pressure. At the same time, because the piston is moving, we assume there should be a force, external force, acting on the piston that prevents the cylinder or the piston from shooting upwards. So in this case, the system would not be moving. And in order to have the gas being compressed, you are required to have a difference in the force. But we are usually considering the compression is slow. So the system would remain basically in thermal equilibrium. If you do it very fast, the system may not be in thermal equilibrium. So typically, when we are considering the work done in the thermodynamics, we try to keep the system in thermal equilibrium. And when that occurs, it means the gas is being compressed slowly, at least in terms of the energy transfer. At least in terms of the energy transfer, the system is compressed very slowly. If it is compressed slowly, it means the difference of the force would be very, very small, maybe close to zero. On one hand, you need to compress it, so you need to have a force difference. On the other hand, you cannot have it accelerate to a very high speed during the compression. So the force must be quite negligible. The net force must be quite negligible. So that would be the physical argument for the thermal equilibrium situation. But in any case, the force would be close to the external force would be close to that provided by the pressure force. So what is the work done by the force? Work done by the external force. So the work done, if you are trying to compress the gas, let us say the y direction is in the upward direction, and you have a displacement dy. Wow, we do not know what is the actual direction of the dy. The dy may be positive or may be negative. So we just write it as a number or variable. On the other hand, the external force is present in the negative y direction. Is present in the negative y direction. So this would be the work done by the external force, if you like. And this external force would be in the negative y direction, so minus j. J refers to the unit vector along the y-axis. And then dot dy, j. So you have j vector dot j vector, which if you, I don't know if an AMA class has taught this before, but they are basically in the same direction, parallel to each other. So it becomes just F times dy. So here is from the vector operation, F dot dr into F dr. The left-hand side is a vector operation. The right-hand side is the algebraic calculation. So it becomes F times dy with a negative sign due to the difference in the direction. The magnitude of the force is equal to pressure times the area. So here we make a clever trick. Area refers to the area of the cylinder. And when you are displacing the cylinder by a certain vertical distance dy, it refers to volume change. So it actually becomes dV. Therefore, the work done by an external force is equal to this quantity minus P dV. Now, what does that mean? Considering that you are compressing a gas, the external force must be larger than the force inside the gas cylinder. P may not be constant. We are not saying that it is constant. It might be changing. Actually, it probably, well, it is a variable. We have not specified in the whole equation. So P is just a, if you like, a variable. But the idea is when you have the external force pressing on the piston, it compresses the gas. The external force is along the same direction as the displacement. So the work done would be positive. The work done due to the external force that compressed the gas would be positive. Is this justified? Think about it. When you compress the gas, dV is negative. Volume decreases. And minus P dV becomes positive. So the left-hand side and the right-hand side seems to be justified, at least in terms of a sign. When volume is decreased, the gas is compressed, work done on the gas is positive. Similarly, when the gas expands, it has to be a larger force compared with the surrounding. And in any case, when the gas expands, it has to push against the external force. When the gas expands, dV is positive. External force that is trying to keep the piston from shooting up. The piston is now pushing outward, dy. So the gas is expanding and it acts against the direction of the external force. So the external force is doing a negative work done. So the work done on the gas is negative, meaning that the gas is not receiving energy, but actually losing energy to the external force. And of course, if the volume does not change, then work done becomes 0. This is a differential form. This is the differential form. If you want to calculate the total work done, then this would be the equation. Well, okay, once again, integration, something you are scared of. But remember what it actually means by the integration. Suppose, well, actually, we could see it in the next slide, which is a better way to observe the whole thing. Suppose you have a diagram that shows a process. Here, it is an initial state of the gas, where you have a certain combination of the pressure and volume, possibly as well as the temperature. But it is not shown here. And then you try to do something. We don't know what the thing we are doing yet, but once we have done the process, you have the final state. So you have the final pressure and final volume. In between, there must be some process or some combinations of the pressure and the volume. So this trace tells you what is the process for here compressing a gas from an initial volume to a final volume. So this is something we call a PV diagram. Pressure versus volume, a PV diagram. Now, this PV diagram is telling you the amount of work done. How does it work? Remember the equation, or I just write it down at here. P is equals to minus P dV from VI to VF. The idea is like this. Integration from some initial point to some final point, y dx. The idea of this integration means that you are finding the area under the graph y as a function of x, or fx, y equals to fx. Y dx basically, well, if you rewrite this integration, I remember I mentioned something before. This integration actually refers to the sum of many small rectangles, or I draw it on the diagram at the bottom right-hand corner. You could consider it to be the sum of many small rectangles under the graph y time, y is the height of this column. Dx refers to a small interval for each rectangle. So you are adding up all the area of this rectangle from the initial point to the final point. So basically, it refers to the area under the curve. All the integration have this physical meaning. It is the area under the curve. Just one thing. It depends on where you start and where you stop. If you start from a small value of I to a large value of f, of course, you have a positive area. Area becomes positive. On the other hand, if you start from a large value of I and small value of f, area becomes negative. There is a direction. So here, the idea of the work done, which is given by the equation at the top, it refers to the negative of the area under the PV diagram. It is the negative of the area under the PV diagram. That is the physical meaning of the equation. It is the negative of the area under the PV diagram. Wow. When you consider the area, you always consider a positive value. But here I'm telling you, when we are doing the integration, the direction is important. If you start from a large value of volume, and end up with a small value of the volume, then the area would become negative. Well, you do not need to consider negative values of P at least, because P is always positive. Pressure is always positive. So volume is always positive as well. So that would save you a lot of difficulties in deciding positive or negative values of pressure or volume. And that is the idea of considering the PV diagram. And this is true whether or not the pressure stays constant. And the work done, importantly, the work done depends on the path taken. Think about it in the next slide. Remember, once again, work done equals to negative of the area under PV diagram. Now, there are different ways for you to move from initial state to the final state. Here, all the three situations have the initial volume larger than the final volume, meaning that all the areas calculated in this way would be negative. So all are negative volume. And when you consider it to be the work done, which is the negative of the area, the work done in all these cases would be positive, because area under the PV diagram are negative, so the work done would be positive. The issue is how large is the work done, which one is larger. Again, because the work done is equal to area under the diagram, so how you move from the initial to the final state becomes very important. Compare the three situations. First, we have the initial state, then moving at constant pressure to the final volume. Before, it takes a sharp turn and increase the pressure at constant volume. So in this case, the work done is just this value. okay, negative of the area. But the magnitude is considered as the net value of the area. In the second case, there is a slight difference. First, we increase the pressure at the constant volume. And then at the high pressure, we decrease the volume. So the work done is the total area, which is larger than the first case, because the area under the curve is larger. Finally, here you have the process that would take some middle approach, if you like. So the work done in this case has to be calculated by integration. But as you will see, it depends on the path to decide what is the value of the work done. So that is the idea. Okay. Now, I will take a break about 10 minutes. During the time, I would like you to do something, and that would, once again, be the you reply quiz. So just a minute. So there are two questions in this you reply quiz. They are both concerned with the ideal gas law, which I hope you have learned. You have some idea how it operates. I will give you around actually I may give you around 10 minutes to finish the two questions. You may like to use the equation. Let me see if I could write that here. You may like to use the equation P equals to P naught plus rho G H to do some calculation that refers to the total pressure, which is dependent on both the atmospheric pressure as well as the pressure due to external objects, which would appear in the question 1. So I first would give you around 5 minutes at least to familiarize with the questions. If some help is needed, I may do a little bit of an explanation. Okay, what kind of tip do you want? I have already written the equation that you may need. We would finish it, well, maybe 4:50. Maybe I try to explain a little bit on the situation here for question 1, which I reckon some of you may not have seen the equation. But first I have to know how to write using my iPad. Okay. Anyway, the idea for this question is like this. You're always comparing two situations in the ideal gas law, or most of the time you are comparing two situations, before and after. So the before situation is you have a gas of 1 meter tall, and it is at the atmospheric pressure. So the pressure would be the same as the atmospheric pressure. The pressure is 1 atmospheric value, which is given to you at here. And then you are compressing a gas, not by your hand, but with some mercury, Hg. So you try to pull in more and more of the mercury until at a certain point, when you keep on pouring the mercury, it just overflows. It cannot compress the gas anymore, basically. At this stage, what happens is at the top layer, at the top surface of the mercury, it is in contact with the atmosphere. So at the top surface of the mercury, it has an atmospheric pressure. What about at the bottom of the mercury? Now, the idea is when you are at the bottom of the mercury, which is just on the top layer of the air, then the pressure would be equal to atmospheric pressure plus the pressure due to the column of the mercury, which is given by the equation density times G times, I better not to write H. I better write something else. Maybe here, it is 1 minus H, 1 meter minus H. 1 minus h. Pressure is additive in this case. At the top of the mercury, it is a low pressure. Then you have the mercury column that develops a pressure. Just like you are in a swimming pool. On the water surface, you do not feel any pressure. But when you are at the bottom of the swimming pool, you feel a lot of pressure from water. You do not feel a lot of pressure from the air. Well, actually, you are because of the atmospheric pressure. But inside your body, you have air as well. So they balance. But when you are in the swimming pool, you have the additional pressure due to the water layer on top of you. What about the pressure at the top and the bottom of the air? Now, it is true, strictly speaking, that the pressure at the top and the bottom of the air are different, but it is minimal. Density of air is around 1 meter cube per second, 1 kilogram per meter cube. So it is much, much smaller compared with that of mercury. So we could neglect the difference of the pressure within the gas. We could neglect the difference of pressure within the gas. So we just treat it as one single value. So hopefully this would address some of the question. And of course, you are talking about the same batch of the gas, same batch of air. So number of gas molecules is the same. And the temperature of the gas should also be the same because they are both in contact with the surrounding environment. So hopefully this would address quite a lot of questions already. You should have the density of mercury in your lecture notes. Or if you cannot find it, just Google it. Density, okay. I'm not spending the whole lesson on the question. I may just leave it on, and I will probably have to keep on doing the teaching at the same time. Right. Well, okay, I could just leave the question on while I would really need to keep on with my teaching. So I would end the question at 5:30 if you like, but I really have the lessons to go on. Okay. It's annoying. So we have just talked about the work done. We have just talked about the work done. And let me see. And of course, apart from work done, you could have a transfer of the energy in the form of a heat. And as a matter of fact, just like the case of work done, the transfer of a heat energy also depends on how the process takes place. And here are just some of the different processes in order to transfer the heat energy. In the first example, you have the heat energy that is transferred with a what we call a constant temperature situation. The gas is in thermal equilibrium with the temperature reservoir, and then the hand is slowly raised or lowered so that the piston is moving into or out of the piston. When the piston is moved into or out, according to the ideal gas law, you would fully expect that the temperature to be changed. But during the process, you can do it very slowly. So you could have the temperature or the heat energy that is gradually transferred into or out of the system through the energy reservoir, which is kept at temperature Ti. So here, the temperature reservoir is just drawn as a board, but it could equally be just the atmosphere, where you are putting the whole cylinder into the atmosphere and let it exchange heat with the surrounding. So just to keep the temperature identical to the surrounding environment. So that is one of the possibility in which you could transfer the heat energy into or out of the cylinder to the surrounding energy reservoir. Of course, when a heat energy is added into the gas, you consider the gas as the system. So if the heat energy is added into the gas, Q is positive. If the heat energy is extracted out from the gas, is removed away from the gas, then Q would be negative. And in the this is just the same situation, but now the force is on the hand is reduced, so the volume expands. Therefore, according to the ideal gas law, you expect the temperature of the gas to decrease. In order to maintain a same temperature with the energy reservoir, heat energy has to be transferred into the system. So that is a scenario different from the previous one, where the piston is pushed downward and heat energy is lost to the surrounding. Now, this is a system that would be quite confusing to understand, but it actually makes a lot of sense. The idea is that you have here an isolated system. It is isolated from the surrounding, so no heat energy could be transferred. And at here, you have the gas originally occupying the lower part of the cylinder, and there is a thin membrane between the lower part and the upper part of the cylinder. The upper part of the cylinder is vacuum, which means no gas at the upper part. When there is no gas molecules, there's no pressure on the upper part. Highly unrealistic, but that is the scenario at here, where sometimes it will occur when you suddenly break free the gas into an open environment. So when the membrane between the gas and the vacuum is broken, the gas would rapidly occupy the region above it. But during the process, there is no work done because the upper part is at vacuum, so the gas does not need to push against anything. There's no force at all to push into the vacuum. So there is no work done. And because the system is also isolated from the surrounding, there is no heat energy transferred through the container walls. So in this case, there is no transfer of the heat energy, and there is no work done in the whole process. And later we will know that actually in such a special scenario, the internal energy of the whole system will not change, which means very oddly, in such a system, there is no change of a temperature when the gas is expanding. But it only happens when the gas is expanding into the vacuum. Okay. So as we just talked about, the energy transfer process by heat or by work done all depends on the initial and final states. It depends highly on the initial and the final states, as well as the intermediate process. So the path is very important. You cannot simply determine the work done or heat by knowing the initial and the final state. On the other hand, pressure, volume, temperature, and internal energy could be determined solely by initial and final states. That is why we distinguish state variables from the transfer variables. State variables P, V, T, as well as the internal energy, they are determined by the initial and the final states only. Transfer variables, which are heat and work done, they are process dependent. Even with the same initial and final states, you could have different Q and W. That is very important to know. Okay. Now, with that, we are ready to talk about the main dish, which is the first law of the thermodynamics. As I've said, it is just the special case of the conservation of energy. How much energy that goes in depends on how much energy is contributed from the surrounding. So in the mathematical form, it is stated in this way. Now here we talk about the change of the internal energy. We are not measuring the internal energy of the initial state or the final state. We are considering a process. So you have an initial state moving to a final state. During the process, you could have heat transfer, you could have work done. They would contribute to the change of internal energy of the system. So that is the first law of the thermodynamics. And the first law states that there must be some quantity known as the internal energy, which is determined basically by the states of the system. So you have the state variables, which is the internal energy. And in case the system is completely isolated from the surrounding, it is not possible for any process to take place. You could not apply temperature difference, so no heat transfer. You could not compress or expand the gas, so no work done. In this case, no process basically can take place, and the internal energy could not change. So internal energy change must be 0. And therefore, the internal energy of the isolated system must be remaining constant. We have been talking about the processes which are involving one initial state and one final state. Of course, that is the beginning. And for engineers, we are actually much more interested in the situation where you could bring the system back to the original state. And the idea is quite straightforward. You try to do one process and bring it from some initial state to some final state. What happened next? Say you have a cylinder of gas. Yes, you bring it from initial state and then to the final state. And then what? For an engineer, if you could just do this, bringing the system from A to B, without bringing it back, you would throw away the system because it is not useful. It just worked for once. Consider it to be the car engine. Haha, you throw away the car because the car can only be driven once. You would like the engine to be moving up and down continuously. So actually, you would like to have processes that would allow you to move from one state to the other and then through some intermediate process back to the original state. This would be much more important. This would be much more useful. And that is something we call the cyclic process. So a cyclic process is one which starts and ends at the same point. They have the same starting point and the ending point, but it would go through some intermediate states. The process, it would not be isolated. And actually, as you will see, here we have some different scenarios for cyclic processes, which involve multiple single processes. And notice one thing. It seems that when you are doing a cyclic process, it always encloses some area, except in a very boring way, say in the leftmost diagram, you are just moving from A to B and then back from B to A directly. That is not very interesting. What is more interesting would be a cyclic process that encloses some area. Now, we try to understand what it means physically to enclose an area in the PV diagram. Remember, when you are moving from one state to the other, you are performing work done. What is the work done? Negative of the area under the graph. So when you are moving from, say, A to B in the left diagram, there is work done. Now, from A to B, it is an expansion. Work done is negative. Work done is negative. Because work done is equal to minus PdV. Therefore, if you have an increase of the volume, work done is negative. So it is the area under this graph. And then from B to C, because there is no volume change, volume is constant, 0 work done. From C to A, it is a positive work done. So the area enclosed refers to a negative work done, a net negative work done. work is done by the, say, the gas over one cycle. But think about it. According to what we have just learned, delta E is equal to Q plus W. When you move from A to B and then to C back to A, you are coming back to the first or the initial state. Because you start from the A and then you end up at A, delta E has to be 0. It is the same state. So according to the first law, what does that mean? It means Q equals to minus W. Where does the work done come from? It comes from heat energy. So you are using the process to convert heat energy into work done. Think about car engine. You are boiling the petrol in order to heat up the gas cylinders. The gas cylinder is converting the heat energy into work done. From time to time, it will be coming back to the initial state. So that is the significance of the cyclic process. Of course, different machines or different engines would run different cyclic processes. So this would be a very major topic of study in the mechanical engineering, or actually in all of the engineering processes. So a PV diagram, you will have a cyclic process which appears as a closed curve. And because of the cyclic nature, internal energy change should be 0 because it comes back to the original state. And therefore, Q must be equal to minus W, which means that the work done comes from the heat energy. So you are converting the heat energy into work. Basically, that is the idea. So in a cyclic process, the net work done per cycle is equal to the area enclosed by the PV diagram. The net work done over one cycle is equal to the area enclosed by the PV diagram. So that is the physical meaning of the PV diagram in a cyclic process. But of course, we are jumping steps. We know that the PV diagram, well, in the cyclic process, can take place in many different forms because it can be a cyclic process formed by different separate single processes. Just like in the previous slide, it could be some funny shapes, triangle. It could be a triangle. It could be the funny shape in the middle, or it could be a square. So different processes would give you different cycles, and that would give you different work done. So it is important to know what are the single processes that forms a cyclic process. And in order to do so, we step backward and understand some special single step processes. And these are 4 important single step processes, if you like, under the first law of the thermodynamics. And as you will see at here, they correspond to some special situations of doing the processes. The first one is called adiabatic, which involves no heat exchange with the environment. And the second one is isobaric. Now, the second, third, and the fourth, they are all starting with iso, meaning constant. So what can be kept constant? It can be the pressure that is kept constant, so it is isobaric. It can be volume that can be kept constant, so it is isobaric. volumetric, or it could be temperature that could be constant. So isothermal process. So you have 4 special types of processes in the thermodynamics, and we would have to study them in more details. First, let us take a look at the separate case, adiabatic process. The idea of the adiabatic process is that you would keep Q equals to 0 for the process. So the idea is you try not to have any heat exchange with the surrounding. You try not to keep the heat exchange equal to 0 with the surrounding. In that case, all the internal energy change, delta E, is coming from the work done. So what does it take to have the adiabatic process? There are 2 simple ways to do so. First, you just cover up the cylinder. You just cover up your gas or your system with some thermally insulating material. In this way, it is very hard for the heat energy to diffuse from one side of the system to the surrounding, from the system to the surrounding, or the other way around. So just like you have a thermal flask and you try to cover it up with some thick layers of cloths, so you could keep a large temperature difference, but yet no heat energy could be transferred to the outside. So that is one possibility. The second one is actually quite tricky. Now, heat energy transfer takes time, but the diffusion of heat within the gas is relatively quick. So as long as the process takes place quicker, much quicker than the heat exchange with surrounding, the process itself can be considered adiabatic. One of the examples is spraying the fire extinguisher. When you open the fire extinguisher, it gives out either usually water, but sometimes it may be carbon dioxide, or the hairsprays. When you press the button on the top of the hairspray, liquid comes out or some gas will come out, then it expands. But the process is so quick compared with the transfer of heat energy. It would not allow the heat energy to go into the can very quickly. So at the end, what you notice is that the surface of the can becomes very cold because the heat energy takes time to be moving to the inside. So in that case, you could regard the process to be adiabatic. Not 100% guaranteed, but it is quite close to Q equals to 0 if the time is short. Okay. So when the gas is undergoing a adiabatic process, Q is equal to 0. It applies to a can of a compressed air as well. So you just release the can of a compressed air, it expands to the surrounding, and the gas inside would not have a much chance for the heat energy to come into very quickly. So that would be considered as adiabatic. So when the gas is expanding adiabatically, it would have to do the work. So this work would be working against the surrounding. This would be work done against the surrounding. So where does the energy come from? It must be coming from the internal energy. So here is what it says. If the gas is compressed adiabatically, W is set positive. So delta E becomes positive. If the gas expands adiabatically, just like you are releasing the gas from a compressed cylinder, work done is negative, and the delta E is negative. So the gas of the temperature decreases. That is why you feel the gas container to be cold after releasing some of the gas. So here are just some of the examples for the adiabatic processes. And this is the case we just talked about. Gas expanding to the surrounding. Well, when you are applying the hairspray in the atmosphere, of course, the gas is not working in the surrounding, but you would have a slightly different scenario. Here, you have the gas that is expanding into vacuum. So the gas expands into vacuum. It does not apply any force, so work done becomes zero. On the other hand, when the gas you are using is the gas in the air spray can, it has to work against the surrounding. So the internal energy change would be not zero. Here, the work done into vacuum would be zero. So you have no temperature change in this case. Okay, so for the time being, I would stop at here. And as I've said, I will stop the you reply question at 5:30. So you have some 10 minutes to finish it. At the meantime, I may have to make some announcement. Firstly, we have the second midterm next Monday. We have the second midterm next Monday. The announcement is already on the Blackboard. So please take note on the announcement on Blackboard. And secondly, if you check the Blackboard, you notice something. There is a, let me see. There is a demarcation table or assessment grades, AP assessment grades. Now, of course, when you are doing an examination or a lot of assessments, a lot of quiz and so on, you'll get some marks. At the end, the marks has to be converted into grades. We would calculate the total mark of for you on all of those assessments. For example, you have the midterm, you have assignments, and the final exam. The ratio of various components can be found in, let me see, can be found in the Learn at PolyU. So teaching plan, here we are. This would be the weighting for various components. After calculating the total mark, well, we are not counting all the class quiz, but some class quiz would be counted. I would take basically the highest certain percentage of the highest grades of the quiz for each of you to do the calculation. For example, I would just, maybe we have 10 quiz, we count the best 7 for each of you to calculate the final marks. So after we calculate the total marks, the conversion into grades would be according to the grading assessment table. So here we are. Basically, one important line for the subject, at least, is this one. D is the passing grade for the subject, and F is the fail grade. If your total mark is less than 35, it would be counted as fail. Other grades would be calculated accordingly to this particular table. So things should be quite transparent. You could work out what is the grade that you get according to the performance in assignments, in-class quiz, midterm, and later the final examination. So all the things should be transparent, okay? I have to announce it because I have to make this process transparent to you as well. Right, so for the second midterm, the, let me see. I think the equation is already distributed to you, and you could find it in the Learn at PolyU as well. Of course, if you have any questions, you could ask me tomorrow during the consultation hour. I may be on and off tomorrow morning because of some other meetings. But if you have questions, either you send me email or you leave message on discussion forum and so on. When is the final examination? I think you have received the email from AR. I think you have received the email from AR for the final examination. You could check your, I think the e-student, which is for this subject, I remember is the 15th of 15th of December. Okay, for the teaching part for today, I will stop at here. So I will stop the recording. If you have any further questions, you may ask me right now.